So let us begin with the fifth problem in this series, and the fifth problem in this series is problem number 1.203. The problem is stating a small body starts falling onto the sun from a distance equal to the radius of the Earth's orbit. The initial velocity of the body is equal to 0 in the heliocentric reference frame. Making use of the Kepler's law, find how long the body will be falling. So this is the scenario that is the problem is discussing, that a body is falling onto the sun. So let us understand by drawing a necessary diagram of the situation. So as we approach this problem, let us first of all understand the usual case. So in the usual case, we consider that the planet is moving in elliptical path around the sun, where sun is situated at one of the focuses, and this is the planet which is moving in elliptical path. And we are considering that A is the length of the semi-major axis that we have. Now over here, the sun is present slightly eccentric to the center of the ellipse, which is the focus of the ellipse, and we mark it as AE from the center of the ellipse, where this is the length of the semi-minor axis marked as B. So over here we say that for an ellipse, E is greater than 0 but less than 1. So in case of E equal to 0, the ellipse will take the form of a circle, and for E equal to 1, that is this case, we say it will take the shape of a flattened ellipse. And in this case of a flattened ellipse, we say that E is approximately equal to 1, where the sun is situated at one end and the falling body is on the other end, which the problem is discussing, and we need to calculate the time period in which it will fall on sun. So over here we can say that if we consider this as approximately equal to 1, then we can say that the sun will start shifting away on this point, and for E equal to 1 it will be just on the periphery of the ellipse, and it will take the shape of an flattened ellipse. So over here we can say if the distance is equal to the radius of the earth, then we can mark this distance as r by 2 and r by 2 respectively. So over here we can say that the length of the semi-major axis is equal to r by 2. So over here if we apply Kepler's law, so we are using the expression t square proportional to a cube, or cube of the semi-major axis, and therefore we can write it as t2 by t1 equals r2 by r1 to the power 3 by 2. And therefore if we take r2, then it is equal to r by 2, and this one is r to the power 3 by 2, and we get the value 1 upon 2 root 2. Therefore we can write t2 is equal to t1 by 2 root 2. Now the time taken by the body to fall onto sun. So here we have calculated the time period with which this body will be completing its trajectory. Now the time to fall onto sun is half of this time, because it is going to fall on sun in half of its time period. So therefore we can say time taken by the body to fall onto sun, time taken by body to fall onto sun is going to be half this value. So over here we write it as t1 upon 4 root 2, where t1 is equal to 1 year, or we take it as 365 days. So therefore if we solve for this time, then we can say the time when it is falling onto the sun is equal to 365 divided by 4 root 2 days, and on solving we obtain 64.5 days, which we approximate to get the answer which is provided in the book to 65 days. So this is the required answer for this particular problem. The thing which we need to understand in this problem is how the elliptical orbit is going to vary mathematically with E approaching 0 and E approaching 1. When E is approaching 0, it will take the shape of a circular path, and will E approaching 1, it will take the shape of a flattened ellipse. So the extreme point of which will be the planet and the sun. So this is how it is going to take the shape, and then we solve this problem using this length, which will become the length of the semi-major axis in this scenario.